people who have a lightning talk, please go to my colleagues on the left-hand side and queue up in the order of your poster or your board number, which is on the list. Then you'll be given 1 minute, and the presentation will be displayed to you in front. So good luck to everybody, and I recommend you look at the posters next door after this session. Thank you.
Hi everyone, my name is Mauro Núñez from INVAP. At INVAP facilities in Bariloche, in the Patagonia, Argentina, we have a upgraded design, manufacture, and run all the acceptance tests on a new stacks monitor. This equipment was manufacturing following a strict quality assurance plan, and then it was calibrated with radiation sources following the stacks project requirement. The equipment is now ready to be shipped, and it will be installed at La Reina Research Reactor soon. And once installed, it will be the second stacks monitor in South America. So if you want to learn more about this project, please join us at Ceremonial Salt, poster 136. Thank you.
Hi, I'm Ansgar from Sienta. We built these sauna systems. You can also see us downstairs. We analyzed the Sauna Cube array. And as you might know, the Sauna Cube is a radio-xenon system, but has smaller and cheaper than the big Sauna 3 that's used at the IMS stations. And so we can build an array of stations which is better for detection probability and also source reconstruction. So here we look at a hypothetical scenario of an array in Japan and show that we can determine the installation order to improve detection probability and also showcase the improved source reconstruction as we add more systems to the array. So if you want to look at the results, please talk to me in here or talk to my colleagues downstairs at our booth, where you can also see the cube. Thank you.
Hello, I'm Michael Swanrick from Creary. For collecting radionuclide particles, 0.2, 0.3 microns are very important little particles that are hard to collect. If you can imagine, if you have a 3 micron particle, much bigger particle, and you could agglomerate that 0.2 micron particle with that 0.3 micron particle, you can make it a lot easier to collect these very fine particles. So how could you do that? You could have acoustic waves that at the right frequency and amplitude make this tiny little particle go up and down, shake around a lot, and this particle move very little. Now the question is, if they do hit each other, do they stick to each other? The other question is are they ever going to see each other? So this one's going over here like this, and it never sees this big particle. And so what are the concentrations? What is the probability? So we did some physics-based modeling. We did computational fluid dynamics. We did some FEA to look at that. And come see my poster if you're interested in more information. Thank you.
Good morning. My name is Peter Jansson from the Swedish Defense Research Agency in Sweden. We have revisited the calibration uncertainties in the sauna systems because we noticed that some uncertainties were larger than we expected. So we have dug into this once more to try to understand why they were large, and we have tried to remediate this issue to make them as small as they should be. Well, my poster was disappeared, I think. Anyway, we would like to show you at the poster session what we have done to actually fix the problem and what is important results from this. So please come by the poster if you want to.
Hello, my name is Andreas Karlsson. I am the engineering manager at Ch4 Envinet, the company that makes the Sona 3 and the Cube, the world's best xenon detection systems. In my poster, I will show you how we made the Sona 3 go from great to awesome. We did that by fixing some issues, upgrading components, and modernizing software for robust performance. And if you want to know how we did this, please come see my poster, how we did build the best xenon detection systems in the world. And also come by our booth downstairs to see a live cube waiting for you. Thank you.
Good morning, I'm Peter Bosch from the Dutch National Institute for Public Health and the Environment. We have recently bought a new high volume sampler called the Snow White to measure, to sample particulates. And we installed this in a new location in the countryside where our old Snow White was on the roof of our building in the city area. And on my poster I will show you some changes in the effects of the change in the measuring side. And a very nice new thing in this Snow White, the new one, is that it has an titanium bromide detector. This is the first Snow White with such a detector. And if you want to know how this detector, the first results of this detector, then you should come to our poster. It's in board 8, just right outside this door on that back side. So, thank you.
Hello, nice to meet you. My name is Peter Andersson. I come from Uppsala University and the Alva Myrdal Center for Nuclear Disarmament. We are currently in the collaboration between Uppsala University and the Swedish Defense Research Agency, where we explore the use of segmented germanium detectors to provide high-efficiency coincidence detectors, gamma-gamma coincidence detectors, for radionuclides relevant to the CTBT, for example, lanthanum-140. In this particular poster, which is made by our postdoc, Shabir Dar, we developed a model to be able to simulate the background. Not only the efficiency, but also the background is very important to understand in order to optimize the minimum detectable activity. And the challenge in making a background is that it needs to provide a fair agreement with reality, but it also needs to be computationally low expensive so we can use it many times in the optimization of a detector setup. So if you're interested to discuss coincidence spectrometry, gamma-gamma, or if you're interested to discuss the background, please meet me by the poster. Nice to meet you.
All right, morning all. I'm Rich Britton from the CTBTO. We have a poster about, again, gamma-gamma coincidence. If you've ever had any questions such as how do you improve the reliability and uptime of a system, how do you make best use of your equipment at stations? It's very expensive, and we have these expensive detectors sitting in boxes as spares. How do you improve data for NDCs? How do you improve the sensitivity? And how do you detect undetectable tests on the IMS? You should come and see our poster. Thanks.
Hello, I'm Michael Fox from Pacific Northwest National Laboratory, and I have a poster on a new system we've been developing for laboratory measurements. So we have the post-processed radioxenon isotope measurement and evaluation system, and that is designed to take information that we learn from laboratory operation of USL-16 in the past, but also as new systems have come around, we have different requirements for xenon volume that we're going to be seeing in the future, as well as more sample throughput. And so this system is designed to be able to take 4 samples kind of simultaneously, put them into detectors, and then measure those at the same time. So it allows us to have much better throughput as well as sensitivity for those samples, and allows for kind of hands-off operation because it's fully automated. And I'll go through and walk at my poster, I'll walk through kind of what we've done and some of the results that we have initially from the experiment. Thank you.
Hi everyone, I'm Edson Jenkins from AWE. So my poster is on some work I've been doing developing a multi-detector gamma-gamma coincidence system. So I've been incorporating some sodium iodide detectors around the germaniums to capture scattered events and try and increase the detection efficiency of the overall system. So if this is something that you're interested in, come and see my poster. I'll be happy to chat to you about it. Thank you very much.
Good morning, Dragana Stasic, International Data Center, radionuclide performance monitoring. Am I going to see the slide? Where's the slide? Yeah, anyway. So the poster is going to show the results of the comparison that was done between IDC-generated automatic radionuclide reports and reviewed radionuclide reports with the baseline that was generated from 7 participating NDCs in 2024 experiment. The metrics used for comparison were number of peak detections, in the compared reports, then what was the second one? Number of correct identifications of CTBT relevant radionuclides, and the third metrics was a comparison of the activity concentrations in the quantified radionuclides. So the poster shows the methodology, the results, and the lessons learned during the experiment. So if you want to chat more, come see the poster.
Good morning. I'm Harry Miley filling in for Lance Leidy, and I hope they don't have the slide. Good. So Lance has a poster about the development of RASA 2.0, in which we try to put in all the lessons that we've learned in 25 years of operation of RASA, which is part of the IMS. If you come by, you'll see some of the mechanical engineering marvels that are part of this. And this is a bookend to the talk I gave and the talk that Michael Swanwick gave yesterday. Thank you.
Morning, everyone. I am Sung-Young Yoon, and our work focuses on the improving the accuracy of genome quantification in the IRIS pipeline. So, for specifically SPLAC samples. In the pipeline, the X-ray area is modeled as Lorentzian multiplets, as you can see here. And then these are used for weighted least squares method. The method combines X-ray count and also gamma net peak areas. And we found that even one channel shift can lead to substantial deviations. And it depends on the mixture of xenon isotopes present in the sample and also the gamma branching ratios. So this highlights the importance of energy calibration once again. So I invite you to visit our poster to have a discussion about how energy calibration affects the accuracy of genome quantification. Thank you.
My name is Brian Archambault, and so this poster is going to be a presentation on what we call computer analyst. So this is an attempt to use machine learning and deep learning to automate the interpretation of gamma spectral reporting from high purity germanium detectors. In the plot on the left, what you see is just a single spectrum from a barium-133. The single peaks, the blue markers, are what we're looking for identification and quantification. We use those Gaussian peaks to quantify. And then the red peaks are what we usually measure and what we actually see on a germanium detector when we count a sample on the face of a high purity germanium detector. You turn 25 peaks that are useful for quantification into about 86, where a large majority of those just interfere with your signatures themselves. We rely on trained spectroscopists to filter out those false positives to give us reliable results. In the context of the CTBT, that's going from the automated radionuclide report to the reviewed radionuclide report. And we're using and developing tools using machine learning to automate that process to augment some of those scientists. So on the input of this system itself, we're looking at peak areas at different peak energies, and then we're using semi-supervised machine learning to identify which peaks and nuclides are actually present, and then in what concentrations. We've been able to achieve greater than about 98% accuracy for over 50 isotopes. We're leveraging both interpretability and explainability models to understand the decisions that are being made inside of that model itself, so that we can just ascertain what peaks are reliable for identification and quantification based on decades of trained spectroscopist knowledge. Thank you very much.
Good morning, my name is Silvia Generoso. I work at Ch4 at the French NDC. So in these studies, the objective is to assess the Bayesian inference for use in our operational pipeline. We use the one that is included in FRIR, which is an open source software, which also includes a cost function localization. So in this study, we compared these two methods to our own in-house methods, and we focus on the reconstruction of the source term on the case of real detections for which we know the actual source, and we also explore the use of ensemble meteorological data to define the model error. So we are pleased to share lessons learned. Come and see our poster. Thank you.
Good morning, my name is Arend Harms. I work for the CTBTO as a radionuclide analyst. Our poster is about interference in gamma spectrometry, the interference between natural radionuclides and those induced by neutrons interacting with the detector or the shielding of the detector, the interference with the detection and the quantification of CTBT relevant radionuclides. Some examples include, of course, lead-212 and its progeny, actinium-228 and protactinium-234N. And of course, we have germanium, copper, and other lead isotopes. And if you come to the poster, I can show you some examples. It may affect the detection of manganese-54, zinc-65, technetium-99M, and barium-140, among others. So please come and have a look at our poster, and I'm happy to discuss it any further.
Hello, I'm Annie Ray from AWE in the UK, and my poster is all about comparing the NDC data we've got with the lab results from all around the world. So initially I wanted to do this with the IMS data, but we've gone for the NDC data just because it was more available to us. So essentially the whole project is just comparing results for different nuclides. So I've looked at beryllium-7, potassium-40, cesium-137 and iodine-131, and essentially comparing MDCs as well as activity concentrations just to see how we can make improvements in the system. So are there any false positives? Are there anything they tend to disagree on more than other isotopes? And just investigating into the differences to see how we can improve on these. Thank you.
Good morning. My name is Anders Ringbom. I'm from the Swedish Defence Research Agency. This post is about the analysis of 2 years of data from the world's first radio xenon array that we have in Sweden. We use this array to address the challenge of locating and identifying release sources in Europe. And you can see on this map the large number of release sources, potential sources that we have. And we are trying to find ways to entangle the data and to try to attribute the different releases to these sources. You can also see the size of the array in green there. So the main results, we have a large number of plumes, many containing multiple isotopes. The array performs as well or better compared to the IMS station. And the main source location depends also on the isotopic composition. Please come to my poster and I will tell you more. Thanks.
All right. Good morning, everyone. My name is Ian Hoffman. I'm from the PTS, and my poster is about modernizing the software that we use to do particulate and noble gas, specifically just high-resolution noble gas analysis. Our software is pretty old. We need to look at making our software modular, able to meet the requirements of the treaty looking at the future. So I want to tell you what design requirements are important. I want to talk about the use of something called NBDev, which is an exciting approach to software development. It has a bit of an iterative approach before you deploy, so that helps make it efficient, reliable, provide good quality software. It works well with our continuous integration and continuous deployment processes. And if you'd like to find out more about our software and talk about some of the requirements we're looking at, please come and talk to me. Thank you.
Hello, my name is Sofie Liljegren. I work at Ch4 in Sweden, and we, as Anders Ringbom just mentioned, have the first xenon array in Sweden, and we are getting a lot of data, and one large problem we have now is we want to optimize the process of sample association. So my poster is about a method we developed which uses two steps, both a machine learning step and then a network algorithm step. So if you're interested in any of these things, please come and talk to me and come and have a look at my poster. Thank you.
Hello, my name is Peter Kindstrand. I'm from the Swedish Defense Research Agency. In this poster, we are looking at automatic alarms for xenon detections. So we have a lot of xenon detections coming in through the NDC and IMS, and in this work we have set up an alarm algorithm to flag both based on anomaly levels and activity ratios. And to try this out, we have run tests with both historic detections from 4 different stations combined with simulated nuclear explosions from our NEMOS system. And running this, we found that we got alarms raised for about 70% of the events. If you want to know more about this, please come see the poster.
Hi, my name is Sophia Brander. I work at BFS, the Federal Radiation Protection Agency of Germany, and I presented a poster in the lightning talk before that about xenon, and a lot of other people also talk about radio xenon, but here I'm presenting Krypton-85, and I want to make a case why it's very interesting to measure Krypton-85 also. We've been measuring it for 50 years, so we have a lot of data that you can see here. And part of my poster is about how, what can we find from this data, how can we really connect it to sources of Krypton-85. And sources of Krypton-85 are reprocessing plants, so it's very interesting from a monitoring perspective. Thanks. I'm happy to see you at my poster.
Hello, everyone. My name is Nick Sidorov. I represent MIX, the Russian noble gas monitoring system developed by VNIA. And today I'll be talking about memory effect in radio-xenon detection. Modern radio-xenon detection system exhibit a low memory effect. For example, the mix plastic detector cell has a memory effect below 5%. However, even such low levels can still influence measurement results, and especially when dealing with the very high activity levels we observed in Ussurisk in 2025. To address this, the gas background must be measured separately and included in the calculation of sample activity. We argue that a proper collection requires an additional calibration for a gas background since its spectrum can differ significantly from that of the sample. The only reliable approach is simultaneous fitting, where the sample and gas background spectra are fitted together using different calibration matrices. More details on the methodology and results are present on my poster, and I will be available for discussion. Thank you very much.
Good morning. My name is Mustafa Smailu. I'm working with the Higher National Authority of Atomic Energy of Niger. So my poster is on assessment of anthropogenic radionuclide detected by the International Monitoring System in the West African Sahelian Band. So the main objective of our work is to determine the activity concentration of anthropogenic radionuclide detected by the IMS station, which are installed in 2 countries of the Sahel. So this is a NEP 48 and the MRAP 43 in Mauritania. One in Niger, one in Mauritania. So the information could be used for future assessment if there is any radionuclide contamination is detected in such a region. So this is the work. For full details, I invite the assistant to come and visit our poster, which is on P3.6 200. Thank you.
Hello everybody, my name is Modignan. I'm from Senegal. I'm part-time lecturer at university and nuclear safety and security inspector at RSN. Today I will talk about the impact of nuclear civil activation application in the EMS station. The goal of this work is first to assess the impact of medical isotope facility located in the southern hemisphere, and secondly, to estimate the appearance of daily release for its facility, and finally, to figure out the strain source if in this area. If you would like more information about my work, I invite you to visit my poster. Thank you very much.
Hello everyone. My poster is about intelligent xeno sampling process in response to the demand for high sensitivity monitoring atmospheric radioactive xenoisotopes. This research integrates an online mass spectrometer with a microgas sampling device, achieving a comprehensive online monitoring system capable of semi-quantitative real-time detection from ppb level to high purity. The core lies in establishing a collaborative control system between the online mass spectrometer and a programmable logical controller, which can dynamically adjust the adsorption and desorption parameters. The above intelligent dynamic sampling technology is expected to significantly enhance the accuracy and timeliness of atmospheric radio xeno monitoring. Thank you.
Good morning. I'm Vladimir Popov from VX Technology, Russian Federation. In my poster, I present a new approach for xenon measurement, big sample. Usually, OSI and IMS equipment produce not more than few cc of the xenon. In our technology, we can take sample up to 100 cc of pure xenon. And MDC for our measurement for xenon always better than 10 minus 5 power, and that gives to us chance not to measure xenon 133 like usually we can see from the station data, but we can, in all our sample, we can feel all for xenon and measure not only the concentration, no, but measure ratios between these isotopes that are very important for event determination. I think this on my poster, I'm familiar with the all step of our technology, from the sampling till this spectrometric measurement. Thank you.
Thank you very much to all the speakers. This ends the session for 3.2 and 3.6. Can I encourage everybody to go and look at the posters next door at 11? Sounds like there's some very good research. Thank you all.